This video provides an overview of some common metrics used in practice to evaluate prediction models. In evaluating our models, we want to assess whether they are able to reliably generate accurate predictions that can provide utility in practice. Whether we are predicting a continuous valued variable or trying to classify a categorical variable, it is important to choose the right set of metrics to fully characterize the strengths and weaknesses of a model. In most cases, evaluation metrics are calculated by comparing a set of model predictions to a set of established actual values. Depending on the context, the actual values may be referred to as y, as the label, as the class or dependent variable, or ground truth, although this then intersects the topic of validity, which we will not get into just now. Conversely, the model's predictions may be referred to as y hat, p, the estimates or probabilities, all depending on the context and the prediction task. When deciding on which metrics to apply, it is generally recommended to identify common metrics that have been used previously in whichever context you're planning to use or report your model's results in. Otherwise, it's recommended to report on multiple metrics that measure different aspects of your model. While you may be limited to metrics that use continuous valued predictions if your dependent variable is continuous, even when modeling a categorical variable, it is recommended that you utilize metrics that use both the continuous valued probabilities as well as the rounded predictions. We're going to talk a little bit more about this later in this video. So while not fully comprehensive, this list represents some of the most common metrics used to evaluate prediction models in educational contexts. Without going through all of these metrics, which would result in an exceedingly long video, let's focus in on some notable metrics here. At a very high level, you can feel free to take a screenshot or refer back to this slide for this reference guide if you're looking for some basic detail on how to interpret each of these metrics. Within this video, we will introduce the highlighted metrics here. First, for categorical variables, for categorical labels, accuracy is among the easiest of metrics to calculate and understand. To calculate accuracy, we simply need to take our model's predictions, which often are produced as a decimal valued probability, and round either up or down to create a rounded classification. Accuracy is then simply the number of rounded predictions that match the actual label divided by the total number of samples. Now within this, as with any metric based on a rounded prediction, there is also a caveat as to how to apply this rounding step. While traditionally, one might think to use 0.5 as the rounding threshold, that is, if the prediction is greater than or equal to 0.5, round up, otherwise round down. In cases where there are large imbalances in your labels, 0.5 may not be the optimal threshold for rounding. Similarly, when there are large label imbalances, accuracy may be misleading. It is for this reason that it is not generally recommended to use accuracy as a primary metric of evaluation unless pairing it with some other baseline model, which will be discussed in the next video. Root mean squared error is a measure based on the continuous valued predictions and is a common metric for both continuous dependent variables as well as categorical prediction tasks. RMSE is calculated by subtracting the actual label and the predicted value, squaring it to remove directionality. In other words, it doesn't attend to whether your model is over-predicting or under-predicting the actual value, and then calculates the mean of this squared error over the entire set before applying a square root to rescale the value. This metric provides insights then into how close your model's predictions are to the actual values. For example, in a binary prediction task where the labels are perfectly balanced, RMSE with values that are close to 0.5 indicate a very conservative model, which makes predictions toward the middle of the probability range. For a continuous valued variable, for a continuous dependent variable, the RMSE provides an interpretable value of how far the model is from predicting truth. For example, when predicting something like a test score, an RMSE of 6 would mean that the model is, on average, about 6 points off from the true score, which may or may not be an acceptable error margin depending on what you intend to use that model for. R squared is another common metric used for continuous valued prediction tasks. It is sometimes referred to as the coefficient of determination and can be interpreted as the percent of variance in the dependent variable that is explained by the model. For example, an R squared of 0.8 means that your model explains about 80% of your outcome. This further means that there is some set of features that are not included in your model that accounts for the remaining 20% of what your outcome is measuring. This could be a set of features that could never be reasonably measured, such as if the student missed breakfast the particular morning on which the data was collected. But it might help in identifying how important the current set of features are in predicting the target as a whole. For categorical prediction tasks, many metrics are based on some calculation of true and false positive rates. In all of these cases, like accuracy, these metrics rely on a rounded prediction and may be sensitive to imbalanced label proportions. On the surface, precision and recall have similar calculations, but rather complementary interpretations. Precision is inversely related to type 1 error. If the model is making a large number of false positive predictions, it will exhibit lower precision values. Recall, which is sometimes referred to as sensitivity, is inversely related to type 2 error. It's a measure of how well the model was able to identify the relevant cases in the dataset. If we are predicting something that is very important to identify, such as high school dropout, for example, we may consider both of these metrics in tandem. Recall tells us how many dropout cases we were able to actually identify, while precision gives us an understanding of how many false positives resulted. In other words, if we always predict that students drop out, we will identify 100% of the cases of dropout and have high recall, but at the cost of high false positive rates, which results in very low precision. Cohen's kappa is a measure of inter-rater reliability or agreement and is often used for observation coding in other fields. As it relates to prediction modeling, it acts as a measure of accuracy that accounts for the base occurrence rates of your labels. Used for categorical prediction tasks and using a rounded prediction, kappa can be interpreted as model accuracy or agreement above random chance. It is calculated using the true positive, true negative, false positive, and false negative values, similar to that which we saw with precision and recall. By accounting for the frequency of actual and predicted values, it accounts for the agreement that is likely to happen due to random chance. A kappa value of 0 in this case indicates that the model is performing no better than random chance, while a value of 1 indicates perfect agreement. Negative values of this metric indicate disagreement, though in prediction modeling any value below 0 is typically considered as poor performance or otherwise could be indicative of a mislabeling error. As the interpretation of kappa is agreement above chance, a kappa value of 0.2 would mean that our model is effectively 20% more accurate than what would be expected if it were randomly guessing in proportion with each label. It is important to note that certain fields and contexts apply certain rules of thumb to define levels of agreement as slight, fair, moderate, and substantial. But particularly in prediction modeling, it is not recommended to follow these scales, as the goodness of a model will largely depend on a number of contextual factors, such as its intended use, but also how the labels are generated and some other contextual factors around that. One of the most common metrics to report in prediction modeling is that of AUC. AUC, or the area under the receiver operating characteristic curve, isn't quite as easy to understand as accuracy, but has a lot of great qualities that often positions it as a primary metric for many prediction tasks. Despite this, there is a clear interpretation for the metric, and it can be calculated using a deceivingly simple algorithm, I'll call it. So AUC, in its kind of typical form, is used for binary prediction tasks, although it can be extended for multi-class classification. The metric uses the unrounded probability, so it distinguishes itself from some of the other metrics we've looked at. It's using the probability that's produced by the model, which avoids the shortcomings of accuracy, precision, recall, and kappa. In fact, AUC, or more specifically the receiver operating characteristic curve, is often used to calculate the ideal rounding threshold for a model. The metric is effectively the integral of the curve produced by plotting the true and false positive rates at all possible rounding thresholds. However, if this sounds confusing to you, and you're certainly not alone, there is a more direct interpretation. Simply put, AUC is the probability that a prediction for a positive label is higher than a prediction for a negative label. In other words, ideally, when given a sample that should be labeled as 1, we would hope that our model makes a prediction that is generally high. And when given a sample that should be labeled as 0, we would hope that our model makes a prediction that is generally low. We don't really care where those predictions occur on a number line, nor how far apart they are, so long as the model is predicting higher for 1s and lower for 0s in our binary prediction task. It suggests that the model is learning how to distinguish these labels. If we wanted to avoid integrals, we can calculate AUC by creating a table. We split our data based on the actual label and place the predictions for all the 0s on one axis and the predictions for all of the 1s on the other axis. For each inner cell of our table, we compare the row and column predictions. If the positive class prediction is higher than the negative class, we place a 1. If the opposite is true, we place a 0. In cases where we have predictions that are equal, we insert a 0.5. We can fill our table and then take an average of all of these values, and that yields the AUC value. AUC is bounded between 0 and 1, where 0.5 is considered random chance, and higher scores indicate higher performance. So now that we've looked at a few different metrics, it's important to emphasize that choosing metrics will depend largely on the task. But again, it's always useful to report multiple complementary metrics to characterize different aspects of model performance. For example, AUC, kappa, RMSE, and recall are some of the most common metrics that I personally use for categorical prediction tasks. AUC provides a measure of how well my model is able to discriminate between the given labels, while RMSE acts as a measure of confidence. The two together help me understand how skewed my rounding threshold may be, which is maybe further indicated by kappa. If I have a high AUC and a low kappa, for example, it provides further justification for maybe using the ROC curve to find a more optimal rounding threshold. But of course, others may commonly use other labels, or other metrics rather. F1 score, for example, is another common metric used in practice, which is just the harmonic mean of precision and recall, combining these two metrics into one. It is important, again, to identify metrics that describe different aspects of your model, but also it's important to identify metrics that will be recognized and understood by your intended audience, if you are tasked especially with describing how well your models perform.